people? Yeah. Okay, so let's talk about this. So the first property. So what do you think about this? So let's talk about how would you interpret this and what do you think it's equal to? Why is it 0, Caleb?
Because there's like no interval. It's just a stick.
There's no interval.
Yeah.
Okay. Right. According to our definition, what is this supposed to be? I mean, this is supposed to be the area underneath the graph of y equals f of x and above the interval from a to a. So it's literally the area of this line segment. And what is the area of a line segment? 0. Okay. Next property. So how do you think we should interpret? So far, all the functions have been positive, right? So what happens if the function has negative values? So interpretation. Okay, so the idea here is that if in general, if I have an integral we interpret this as area above the x-axis minus area below the x-axis. The reason being is because how we define the Riemann sums, we don't make the height absolute value. When we add up the areas of those rectangles, we keep the height at whatever the function value is. So rectangles that dip below the x-axis are interpreted to have a negative height, and then that obviously then gives them a negative area. So it's area above the x-axis minus area below the x-axis. So this has an obvious consequence that areas can cancel out, right? So an integral can end up being 0, but that function is not 0, right? The function just is such that the area is canceled out. For instance, I can have, let's draw a function that's not 0, but whose integral is 0. What would that kind of look like? That might look something like maybe that. Right, here's A, here's B. Right, so these two regions that are above the x-axis, those are counted as having positive area, but the area that is the region that is below the x-axis, that is counted as having negative area. So that's positive, and this is negative. So in this case, how I've drawn it, the two positive areas seem to kind of cancel out the negative area, right? The two positives together, it seems to be about the same area as the negative area, but they cancel each other out because one is negative, the other is positive. Okay. Jacqueline, can you give an example of a specific function that you think might actually have this property? It's a non-zero function, but the integral ends up being 0. Can you give me a function and an interval where that happens? You have an idea?
Maybe sine. I don't know what interval, but
So maybe something like sine of x.
Yeah.
So probably maybe something from 0 to 2 pi. Because if you think about that, right, from 0 to 2 pi, it's like that, right? The stuff above should cancel out the stuff below. So that's an example of such a function that would have a 0 integral. Okay, next property. It's called the linearity property. There are two things here for linearity. So first of all, if I have the area underneath a sum of two functions, So if you stack rectangles on top of each other, you can always unstack them. I can always just say, do the integral of each function separately. So that should make intuitive sense to you, right? You can either stack the rectangles separately, or you can stack them on top of each other. You still get the same exact area. And now this property, if I have a constant times a function, what does that constant do? That constant would only end up doing what? It scales all of the heights of the rectangle. So it would stretch out all of the rectangles. That's the same thing as computing the areas of the rectangles to begin with, and then multiplying everything by that constant c. So constants come in and out of integrals. And then one last property, which is called additivity. So if I have the integral of f from a to b, and I add the integral of f from b to c, what do you think that should end up being? We can actually combine these two integrals into one integral. And what one integral do you think we would do? Cross multiply. What does that mean, cross multiply? What the hell does that mean? A to C. Okay, good. And if you want to understand where that's coming from, let's see, I think I already have a picture. So what does additivity mean? Well, additivity means exactly this. So the green shaded area is equal to that integral from a to b, right? And then I'm going to add to it the integral from b to c. That's the blue area. But green area plus blue area makes what? Makes the pink area. So in other words, if you have two regions that are next to each other, you can just add up the area and get one big area. I mean, that makes sense, right? I mean, that's not supposed to be